So this video is to introduce you to arc length, now not just of plane curves like you learned last year, but arc length of space curves. And that's section 13.3. So last year in BC Calculus, you learned to calculate arc length of a parametrically defined curve from t equal a to t equal b would be given by this. T equal a to b, the integral of dy over dt squared plus dx over dt squared dt. Or maybe what you remember is arc length of a function in terms of x is this, where x is equal to a and x is equal to b. And both of these things are connected to one another. So this is like your last year work. If this is the one you can remember, I can take you back to that one from there. Actually, I'll just show you the other direction. It doesn't matter which one I show you, but these two are very closely connected. If I take this integral and let's say I'd like to divide by dx over dt squared under the radical. And the reason why I chose to do that is I'd like to turn it into having a number 1 right here. So if I divided by dx over dt under the radical, I really divided by dx over dt overall. So I'll multiply by a dx over dt on the outside there, and then really haven't changed anything. Now notice what happens here. If we play around with differentials a little, these dt's cancel. And what I have here then is in terms of x. So then these values need to turn from t values to x values. I see I've got the number 1 here, and then dy over dt divided by dx over dt is going to give me dy over dx squared right here. And so this integral can turn right into that one. So no matter which one you remember, if you remember one of those two arc length formulas from last year, you remember the other. Now, when we're dealing with arc length last year, we were in 2 dimensions. We were talking about a plane curve. And we said they were called parametrically defined, right? Now we're talking about a space curve. And that's going to be given by a vector valued function. And that vector valued function might be, for example, r at t, and have component functions f at t, g at t, h at t. Well, if we want to find the arc length on that vector value function, r of t, from t equal a to t equal b, I don't think it's hard or earth-shattering for anybody to know that you're just going to need to have 3 dimensions in here, right? So these are going to be values of t, and it would be dx over dt, that quantity squared, plus dy over dt, that quantity squared, plus dz over dt, that quantity squared, if we're talking about a curve in space dt. And that would give us our arc length if these were values of t, a and b, where we're going to let our x component be f at t, our y component function be g at t, and our z component be h at t, right? So that's what these x, y's, and z's are up here. That can be written a lot faster by looking at the fact that what you have here is a square root of components squared, Or in other words, the magnitude of a vector. The magnitude of a vector with components dx over dt, dy over dt, dz over dt is what's sitting under that radical, magnitude of that vector. And that vector, which is the derivative of the x component, y component, z component, to give you a new vector valued function, is the magnitude of r prime of t. So a faster way to write this arc length calculation is from t equal a, t equal b, the magnitude of the tangent vector dt.